Okay, so let's continue. I'm looking for my remote control. Yeah. Okay, so as I mentioned, we want to talk about first law of thermodynamics. That will give us ultimately, that will give us the temperature. So we can write, so we look at an adiabatic system at constant pressure. So this means dq is 0, dp is 0, and we only have reversible work. So dw is minus pdv. This is the first law here. du is dq plus dw. And so dq is 0, dw is minus pdv. And dh is by definition, h is u plus pv. So dh is du plus pdv plus vdp. And so if for du I use the first law here, then I get here minus pdv plus pdv. This goes away. We're looking at a constant pressure system, so dp is 0, so dh is 0. That's what I said earlier. In a constant pressure system, first law of thermodynamics, adiabatic system, first law of thermodynamics will tell you enthalpy stays the same. Okay? Now, we can use that and to compute the flame temperature. If we say I can integrate this relation here from unburned to burned, and it just tells us if I have a system, let's say I have a box. No, not a box. Box would be constant volume, not constant pressure. But let's say I have a constant pressure system, fuel and air, unburned, and now I burn it. The composition, everything changes, but the temperature changes, but the enthalpy is still the same. Okay? So, HU is equal to H burned, H unburned is equal to H burned, or now, this is the enthalpy of the mixture. I can introduce here I can relate this back to mass fractions and so on. This here I know, the mass fraction of the unburned I know, because that's what I put in my constant pressure box. And the enthalpy here, that's function of temperature and the composition, and these HIs are just function of temperature for each species. The temperature I know is my initial condition. Okay? So the left-hand side here is totally known. The right-hand side now, you see, in the last lecture, we determined all the burned mass fractions. We got this from this Burke-Schumann solution. You fix the mixture fraction. Then I can tell you what the mass fractions are in the burned state. If we assume fast chemistry, complete conversion, and then this here is just a function of temperature. So you see, this here, everything is known except for the temperature, so this gives us an implicit relation for temperature. You could just take this because the HIs, they are given by these polynomials. So you see you have a fourth order polynomial, and you could solve this iteratively. Okay? So all we do now is basically just have an approximate solution to this so that you can do it. You don't have to do an iterative solution. Okay, so take this, and then the HIs here, they are composed of reference of the enthalpy of formation and the thermal enthalpy. So we plug this in here, and we plug it in here, and then we get four. Now these are two terms. Now we get four terms. Two related to the reference enthalpies or the enthalpies of formation of the unburned and the burned state. So you see I put this thing here from the right-hand side to the left-hand side. And then two of the two terms with the sensible enthalpies here from the burned and from the unburned. Okay? Okay, and the heat capacities here, they're just temperature functions again. So we first want to look at the left-hand side. You see here the left-hand side. Left-hand side, how can we express this? We can use coupling function. So use the coupling function integrated gives you this. Y unburned minus Y burned is equal to, of any species can be related back to the same change in the fuel. And you see, I take this thing here, is the same as this here. for all species. So I take this equation, I multiply it by the reference enthalpy of each species, and I sum it up over all species. Okay? And then I get this. Okay? Just multiply by href and sum over all species, and then you get this. And you see, now this here is the left-hand side of this equation, is given here like this. So now I related the change of all species that we had here, mass fraction of all species, I related it back to the change just of the fuel. And that's simple here because, at least for stoichiometric conditions, let's say we know your fuel and the burnt here 0, and so on. Okay, so now you see you have the sum here of all these reference enthalpies. And the sum of all the reference enthalpies here, that's what we call the heat of combustion. Okay, so you could say this sum here, it's the sum of all reference enthalpies. Some are positive, some are negative. But if I sum all these up, or you could say this is basically it's the difference of the enthalpy of the products minus the enthalpy of the reactants. Because this stoichiometric coefficient here is positive for the products and negative for the reactants. That's what we said earlier. And that just gives you the change of enthalpy, or formation enthalpy, over the reaction. So we call this is the heat of combustion. Okay? You see this is a function of temperature, but it turns out while all the enthalpies, individual enthalpies, they change with temperature, the sum of all these, the heat of combustion, it changes very little with temperature. So we can evaluate this term here. We can evaluate it at a constant temperature, the reference temperature. Now we assume the reference temperature here should be the unburned temperature that we had in the beginning. We want to assume the CPs here, they are constant because we burn with air. It's mostly nitrogen, let's say. So we want to assume it's 1.4. That would be the same as air. Okay, so these are the assumptions. And if I make these assumptions, you see if I assume the CPs to be constant and equal here, then this is the integral from Tref to Tb minus Tref to Tu. So the Tref goes away. This is just the integral from Tu to Tb. And I can just integrate this if I assume Cp is constant. So the right-hand side is just Cp times Tb minus Tu. The left-hand side we evaluated earlier. We say this here is just Q, the heat of combustion. And, you can just solve this for Tb minus Tu, and that gives you this. And you see here, fuel unburned, that's given. That's your initial condition. That's how you mix it. Nu F here is from the global reaction. Cp, we assume constant, 1.4. Wf is given for a specific fuel. And the Qref here, go back to this. It's just Qref. It's just nu times Href. And the reference enthalpy of formation, they're tabulated. You can find them in the table. Okay? So it's very easy, actually, to compute this. It's very easy to compute this once you fix your system. So that tells us what the temperature is at complete conversion to products. Okay, for rich mixture, we related everything back to oxygen. For rich mixture, we should relate everything back to, we related everything for lean mixture. We related everything here back to the fuel. Why? Because the fuel at complete conversion for lean mixtures is 0. This here is 0. This here is given. So this here is a very, very simple relation. I can compute YB for any species very easily. In the rich mixture, this would still be valid, but now I need to know YB. So it's easier to use the coupling function with oxygen for the rich mixtures because the rich mixture is oxygen 0. Okay? So if we do that, here we just use this coupling function, and then you plug it in here again, and now it's related here to YO2 instead of Y fuel. Okay? So we have one for lean, one for rich, and of course, at stoichiometric, they should be the same. And you can see this easily, that they are. Okay, so interesting now is I can take this for lean and for rich, and I can write it in terms of mixture fraction because you see I have YFU and YO2 unburned. I can relate these easily back here to mixture fraction, and I can express the temperature as function of mixture fraction. Okay? So just plug in these expressions here for fuel and for oxygen. And then I have TU. TU is just is the unburned temperature at a given mixture fraction. Think again, you have a fuel stream and an air stream, and you mix them together. So this here is just the mixing temperature of both of these, assuming that Cp is constant, otherwise this wouldn't work. But so I use this here for Tu, and then I get this expression here for lean and this expression here for rich. Okay, and you see again all these terms they're given. I mean trivially. I mean this is all. You can make up your case and compute this right now. If I would give you Q. Q is the only one that you don't have in front of you right now. Okay, so it's trivial to compute the burnt gas temperature. So maximum temperature here appears as C stoichiometric, and is given like this. So now I can plot this again in the same graph I had earlier. This here is now temperature as function of mixture fraction. You see again I get linear relations here in the lean and in the rich. You see this is this unburned temperature. It just says this is the oxygen temperature, this is the air temperature, and if Cp is constant, then the mixing temperature is just straight line. Reality is not the case. Cp is not constant, and the enthalpy actually, that enthalpy is just mixes like this, but as linearly with mixture fraction, but because enthalpy is linear, but Cp is not. Reality is not a straight line, but let's say it's close to a straight line. Anyways, this is what you get, and this is the last ingredient here to this so-called Birch-Schumann solution. Okay. So now you can, without a computer, really, if I give you the value of mixture fraction, or let's say you do solve the mixture fraction equation on a computer, which is simple because it doesn't depend on chemistry, really. You can you tell me what temperatures, what mass fractions are, and so on. Everything just from these simple relations. And it's not so bad, actually. It's not a bad approximation. Okay. Right, I wanted to ask you one more question, I forgot. This is just here table of different fuels, the stoichiometric mixture fraction, this combustion with air, and you see they're all very similar, 0.05 to less than 0.1. And stoichiometric temperature here, 2,200 something. The true equilibrium temperature is more like 2,220 for methane, 2,223. So you see, we assumed that, and that was a comment we had here earlier. In reality, you don't have complete conversion. You will never convert everything to CO2 and water. You will just go to equilibrium. What the equilibrium concentration is depends on the conditions, but you see it's quite close to equilibrium, actually. It's quite close to the complete conversion here. You wouldn't make a 40 Kelvin difference. You have to keep this in mind, but is not so bad. Right. And then I thought actually we had, the tables. Okay, so the only thing that's missing now is the QREF. But the QREF depends on the HREF. And the HREF is on a table, and we'll get to that table later on. We all put it, there are other things in the table, and we just put it all together in one table. Okay, any question about this? Okay, so then let's talk about second law of thermodynamics. The second law I mean, the assumption of complete combustion is an approximation, as I just said. In reality, you go to chemical equilibrium. And if we, sometimes, as I said, you go very quickly to equilibrium, and sometimes it takes just forever, okay? In a flame like this, many species, many reactions are actually at equilibrium. If I light this thing, they're almost exactly at their equilibrium value. But of course, you see this at low temperature here, the table or the floor and the air, they're not at equilibrium, and it will take forever for them to reach equilibrium. Okay, so how fast so equilibrium will tell you where things want to go, okay? And the thing is, you cannot do anything about it. You cannot change this. The only thing you can change it is by changing conditions. You know, thermodynamic state for a simple system is determined by two independent intensive properties. Everyone should always, keep this in mind. So if I fix the temperature, if I fix the enthalpy and the pressure, things will go this way. You cannot change it. You can change the pressure, you can change the temperature to try to modify things, but you can't do anything about it. So how then, what if you use catalytic reactions? For example, you have an exhaust gas after treatment. How is it that combustion produces a lot of NO, but then the catalyst, the three-way catalyst, will just, convert it back to oxygen and nitrogen?
Because you're at a lower temperature and you're utilizing the equilibrium concentration at that temperature.
Right.
Simultaneously, the catalyst is reducing the activation energy.
Right. So what you do in the catalyst, we'll see this later on, you are in a temperature range where the equilibrium is that you have no NO, that it's all N2 and O2. But at the same time, you would never go there because, like this, chemistry is very slow. So the catalyst just reduces activation energy, or it makes the reactions fast, but it just drives it towards equilibrium. A catalyst cannot reverse the direction of where a reaction wants to go. It can just make it faster towards where it wants to go anyways. Okay? It's very important to keep in mind things want to go to equilibrium. If you have concentrations lower than equilibrium, they go this way. If you have higher than equilibrium, they go this way. But you can't do anything about equilibrium. You can't do anything about thermodynamics. Thermodynamics is very important in life for you, everyone. I mean, I teach thermodynamics course. I tell people if you don't understand entropy and second law, you're not equipped to live, really. Your life decisions, they should always... when I make a life decision, I think of the second law. I write it down, do entropy balance, seriously. And usually, you make good decisions by doing that. So, talk about decisions. Professor Law was saying yesterday he chooses the lecturers because they're the world-class best lecturers. No. He chooses lectures by who says no and who says yes, I'll do it. That's so I made my life decision. I've made a mistake in my second law of thermodynamics. That's why I spent this week here. Okay, no, I'm joking. I enjoy being here. Okay, good. So equilibrium, very important. Things try to go towards equilibrium. How fast things go towards equilibrium is determined by kinetics, but, and again this is very important, the equilibrium state, it does not depend on kinetics at all. The equilibrium state doesn't know, and it doesn't care about kinetics, okay? Just how fast you get there, that depends on kinetics. Okay, so kinetics are very important. Some things are in equilibrium, others not, and we need to worry about this in combustion. Kinetics is dealt with in the afternoon. We'll just talk here about equilibrium now. So, you can assume chemical equilibrium, and the second law of thermodynamics will then tell you, if I assume things, I put a piece of this thing here with air in a box, okay, and then I let it go to equilibrium, then the second law of thermodynamics will tell me exactly what the concentrations are at the end, okay? I can compute this, and we'll see how, again in an approximation, how we can do this, but that could be a model also. Then you don't need to worry about kinetics at all. Sometimes that's not a bad assumption, actually. When temperatures are high, you know, for hydrogen diffusion flames, not so bad. Turns out for hydrocarbon flames, it's a really bad assumption. For lean combustion, it's not so bad, but for rich conditions, it's really bad. Because in rich conditions, you form a lot of intermediates, such as CO and H2, and you know, that are kind of stable, but they're not in equilibrium. Equilibrium would tell you something totally different. So still, although it's not good as a model for determining concentrations per se, it is an exact thermodynamic limit. We should say at stoichiometric, where things are really fast, because temperature is high, also chemistry is fast, actually equilibrium, that's a good assumption for determining what happens at stoichiometric conditions. At rich conditions, as I just said, is really bad. What I showed you earlier, complete conversion, infinitely fast reaction with complete conversion, that is a much better assumption under rich conditions. So, I mean, is a better assumption. So one has to be careful with all of these assumptions. So, second law of thermodynamics relies on the entropy. Now, entropy is even for an ideal gas is a function of temperature and pressure. Okay, you can use Gibbs equation to relate entropy back to other quantities, temperature and pressure, and you can write it like this. The entropy, we write it like this. Entropy is a term that depends only on temperature plus a term that depends only on pressure. Okay, that is true here for an ideal gas only, but you know, for an ideal gas you can do it. Then this temperature-dependent term, that is very similar now to the enthalpy, where you have an entropy of formation or a reference entropy plus a temperature-dependent term, or plus this temperature integral. Okay, so you have temperature dependence and pressure dependence. Everything else is very similar. Now, the way we determine equilibrium is very similar to the way we determined adiabatic flame temperature, only that here you always also have this, you have one extra term always. Okay, so these reference values are listed in tables again. Now we can introduce the chemical potential. Chemical potential or relates back to the Gibbs free energy. Chemical potential is given like this, and of course, so it's H minus Ts. H now has two different terms. H is a reference enthalpy plus a temperature term minus Ts. Ts has three different terms. One is the reference term. One is the temperature integral, and the third is here the pressure term. Okay, so the point is, now we talk about enthalpy, we have two terms. We talk about entropy, we have three terms. We talk about Gibbs free energy is a combination of the two, so we have five terms. So the thing is not more complicated in a sense. I mean, you know, thinking about it, but it's just a lot more writing different terms. Okay, that's the only difference. So you have these five different terms. Now, chemical equilibrium for a certain reaction, take any of these reactions, could be a global reaction, could be an elementary reaction, is given if the sum here of all the chemical potentials of the individual species, if that's equal to 0. Okay, or basically what it means, if you have a chemical potential of the reactants with respect to the products, then the reaction is not in equilibrium. It will still go in that one direction until the chemical potential of both sides is exactly the same. Then you still have reaction, the reaction goes this way, but it also goes the other way, and the sum is 0, and nothing changes anymore. Okay, so potential, the chemical potential of reactants and products, if that's the same, which means that this sum here is equal to 0, because again, nu here is positive for the products, is negative for the reactants, then you have chemical equilibrium. So now all you need to do is take this here and plug it in here, and that's it. Okay, so conceptually it's very simple, but again you get a lot of different terms. But if we do it, so I take this and I plug it in here, then I get this relation. Where now here on the left, so where what we did now, let me see that we don't get lost here. I said this is the chemical potential, is enthalpy and entropy. This is all in all 5 terms. But you write it like this. We just say also the chemical potential has one temperature-dependent part and one pressure-dependent part. Also depends on temperature here, but let's say this is the pressure-dependent part. Okay? So if I plug this in here, then I can separate these 2 terms. One here on the left-hand side is just this, this temperature-dependent part, and then on the right-hand side here, I have the pressure-dependent part. And that is, so I call the left-hand side here, this thing, I call this the equilibrium constant, you see? And then, so this here I call the equilibrium constant. And then this gives me the law of mass action. So this, the equilibrium constant, that's a nice thing. By definition, this thing here only depends on temperature, nothing else. Okay? So I have this equilibrium constant and the composition. This depends on temperature. And on the left-hand side here, I have something that only depends on pressure. And what you see here, this is actually the partial, this is the reference pressure. It's whatever it is, it's just the reference pressure. This is where I defined, so what is the reference pressure exactly? Look at this. This, again, here we have this SI ref. SI ref now is the reference enthalpy, reference entropy, and it's defined at a certain pressure and a certain temperature. 298.15 and let's say 1 bar. Okay? So P naught here, that's just 1 bar. That's where I defined this pressure. And you see these are, in a sense, they're partial pressures of reactants and products. And you see this is to the power of the stoichiometric coefficient, again, which is positive for one, it's negative for the other. So if I have a reaction, A plus B goes to C plus D, then this will be partial pressure of C to the 1 power, stoichiometric coefficients are all 1, times PD divided by P naught squared, okay? But then I have on the other side, I have now A to the minus 1, so this would be PA, and PB, again divided by P naught squared, so the P naught goes away. So if I have the same moles on both sides, the P naught goes away, otherwise it stays there. But then you see this is just, basically, you can write this now, partial pressures, you can write these as mole fractions. So this would be the same as mole fraction of C, mole fraction of D, divided by mole fraction of A times mole fraction of B. Okay? So that just relates the concentrations or the mole fractions of the products with reactants. So you see, in equilibrium, so what this tells me is if I fix a certain temperature, I can compute this thing, and then at this temperature, it tells me what this ratio is. Okay? So if the K here is very, very large, then I will have all products, no reactants. If the K goes to 0, then I will have all reactants and no products. Okay, and vice versa. And if I change the temperature, that's what you see now. Maybe I change the temperature and the K gets larger. That means now I get more products. Okay? And that's what we said earlier. When you, for this NO reaction, if you go to very low temperature, then the K here gets very small, and K very small means, you know, this, if this was NO, that means I have no NO, I have only, reactants, which would be N2 plus O2, let's say. Okay? So that's what this does. Now, the only thing is you need to compute this, which means you need to compute this. Mu 0, let's see, where do we have it? We had it on the previous page. Here, which means you need to compute this whole thing. Not trivial, this is trivial because you get these from tables. This is not so trivial, and this is not so trivial, okay? But can be done. Now, this is an example here. This is what I just mentioned. Basically, these are equilibrium constants for 3 different reactions, global reactions. And you see here, this here is evaluated then at a certain pressure because these are do not have the same number of moles necessarily. And so the P naught stays there. It depends on the pressure. But what you see here, for example, equation 6, this with increasing temperature, it goes down. Now look at the scales here. It's 10 to the 20, 10 to the 10, and so on. So this means for higher and higher pressure, I will get less products. I will get more reactants. But even at very high temperature here, you know, let's say 2500 Kelvin, this is still, what is this? You know, 5 or so it's 10 to the 10. So this would be 10 to the 3, still 1,000. Okay. So here in this range never goes to the point where it's less than 1. Okay. So maybe if you go here to, what is this? I don't know. You know, 10,000 Kelvin or whatever. Take this reaction here, CO plus H2O. This is the so-called water-gas shift reaction, very important reaction we'll talk about later on. Converts CO to CO2, but at the same time converts H2O back to H2. So you have the CO to CO2, that would be heat releasing, but converting H2O back to H2, that's endothermic, so you need to put in heat. And so this is almost, it doesn't produce any heat, but it produces a little bit. And so you look at this, you see this, I think, slightly goes up in this direction. But it's all, I mean, at least on this scale here, it's almost independent of temperature. So, so it has the same direction as this. It still goes up a little bit, but very weakly. Okay, and you see that the concentrations here. You could maybe this 1 times 10 to the 0. So it's 1. So it's a little less than 1, but it's close to 1 in a sense. Okay, good. Sorry, the third reaction here. That's this nitrogen reaction. O2 plus N2 gives 2NO, and that's we said this earlier. This is here. You see, first of all, even at very high temperature, it's much less than 1. So NO will not be a mass fraction of 1. It will always stay small, but high enough to cause damage. And then when I go to very low temperature here, so this is 1,000, maybe I go to 500 Kelvin, then you see this is 10 to the minus 10 would be the equilibrium. And so if I can make that reaction fast to go towards equilibrium, then all the NO will be gone, okay? But that's pure luck. I mean, that's just because, you know, this is what this reaction is. Okay, so we said this is, in principle, it's easy to use this relation here, but it's kind of hard to evaluate this equation. And so one thing you could try to do, this is done here. I don't want to go through the details, but you can make some approximations, especially here, neglect the temperature dependence of heat capacities, and then you get a very simple relation that you can use to actually, on the back of an envelope, to compute what the equilibrium concentrations are. Let's see what this is. Okay, so this is the definition of Kp. Kp is what we want to compute. Let me show this again. This is the Kp. If we can compute the Kp, everything's good. Okay? So Kp, the definition is this, and you have these mu's here. So let's first look at how does this look like. Mu divided by RT. Okay, you have 1, 2, 3, 4 terms. The pressure-dependent term was on the other side, and so you have these 4 different terms. And what you can see here is that if I write it like this here, I could say this here, actually, so I write these 5 different terms here again. The first one here looks like an Arrhenius term. So this here is a constant, okay, because these are just from tables, divided by RT. So minus some constant divided by RT. That looks like an Arrhenius term, okay? Let's keep this. Not much we can do about this. Then here we have a term that is S ref divided by R. This basically is a constant, okay? So you see the temperature here goes away by dividing by RT. So this basically is a constant. This here now, here we need to do an approximation. This is the next term where you have T minus T ref divided by T. Now, if T is very large, then this is independent of temperature, right? If T is much larger than T ref, I can neglect T ref and the temperature goes away. So large temperature, this would be independent of temperature. We can say it's also almost constant. So for large temperature, these 2 terms are constant. And this one here has the ln of a temperature. This one goes with ln exponential of n times ln temperature. Or you could say is t to the nth power. T to the nth power, something like this, okay? So what we can do then is, because these are all sums here, we can tabulate this constant. We can tabulate this exponent here. We can tabulate, these quantities, and then we can approximate this here, or this whole thing. We can approximate it as this, which is basically here this first term as it stands. But then this here, these 2 as a constant, where we just say, so this is sum of nu times a constant, and this here is nu times a constant. And so we can just tabulate this constant, and we call this pi a for each species, okay? Oh, by the way, there's an I missing here. This should be S ref I, okay? Because the reference entropy is different for each species, so we forgot the I. So I can tabulate this pi for every species, and then here I can write this as, pi b times ln t, or this is basically is this n here that we tabulate for each species. And then if I have these, so I can write it like this. So Kp is like an Arrhenius form now, is b, that was the constant, times t to the nth power times exponential of this. And then I tabulate b, looks like this, n looks like this. So if these pi values, these are tabulated for each species, and h is tabulated, so it's very easy to compute this. Okay, so these are the tables. You see here, there's, for example, let's see here, N2, molecular weight, in case you don't know this. There's the reference enthalpy. A reference enthalpy of N2 is 0. That's what we said earlier. Then you have this SI reference value, and you have the pi A and the pi B. Okay, they are all in the table. Table here for many species. And then at the end of the day, you can just go in these tables for a reaction, evaluate these coefficients here, and then you get the Kp. So it's very simple. So this is just a little approximation to be able to do this on the back of an envelope calculation. You don't need to any iterative solver or whatever. Okay, let's look at an example. Example is green here again. N2 plus O2 gives 2NO. The pi's are given here. You can just compute this B from the table and the global reaction, the N from the table and the global reaction. See, it's very simple. And also this delta H, it's just the sum of all the H's from the global reaction. And then you get this, okay? And this, now law of mass action, so this gives us XNO is equal to some temperature function here. And you see, it looks like an apparent activation energy here. So this is now the partial pressure of NO divided by the total pressure, or just the mole fraction of NO that you get. And you see it has a weak temperature dependency, very weak temperature dependence here, but a strong temperature dependence here. There's an apparent activation energy here of, or activation temperature of 10,000 Kelvin. Everyone knows NO formation has a high activation energy. This is not the kinetic activation energy. This is now the something that looks like an activation energy, but it tells you really the equilibrium. So if you evaluate this now, XNO, NO mole fraction, for different temperatures, you see here for 1500 Kelvin, this is 1 ppm, okay? For 2000 Kelvin, I don't know what it is, but you see this is 2 orders of magnitude larger, so it's very large, which would be a typical combustion temperature. But if you look at 300 Kelvin, it's 10 to the minus 16, okay?
I don't know if you may have explained it, but the pi values that you've seen there, thermodynamically, what is their manifestation?
Yeah, thermodynamically, they're just coefficients in this approximation. Okay, so let me go back here. So we said this is constant, this is constant. Okay, now constant means this is only true for high temperature. Otherwise, this would not be constant. Okay. For large temperature, these, let's say 2000 Kelvin, these temperatures here, Tref is 300 Kelvin. I say this is roughly, unity. And then the pi value, you see, I can write this for each species. And I can say pi, so nu times pi I. Pi I is then the sum of this Cp and this Sr over R. So it's nothing real, okay? It's just within this approximation, it gives me these values. And here, it would be this Cp divided by R. This would be the exponent here to this, okay? So it's nothing real. It's just, it just has meaning within this fit. Okay? And this is what we said earlier then. Look at XNO, the NO mole fraction, the equilibrium mole fraction in the system as function of temperature, inverse temperature. Here in an Arrhenius plot, because, of course, we have this exponential dependence. And then you see the temperature dependence is very, very strong. Okay? This goes here, you go from 2000 Kelvin to here 500 Kelvin is like 6-7 orders of magnitude difference. So this is what you have. Combustion here is at high temperature. If if the temperature is now, this has two temperature dependencies. So if we say NO is temperature dependent, it's really double temperature dependent. And of course, they're related to each other. But first of all, the equilibrium is very, very strongly temperature dependent. Secondly, the kinetics also. So you go to high temperature, then the equilibrium would be a lot here, 10,000 ppm, would be a lot of NO. But, let's say at high temperature, kinetics are fast also. So they're not infinitely fast. So you form NO, and maybe you get close to equilibrium, but maybe in the time you have in a combustor, maybe you only get to here. But combustion equilibrium tries to go there, and kinetics might be slow, so you might end up here. Then in the exhaust, you cool down to something, or maybe in an internal combustion engine, expansion stroke, you go to lower temperature. So now you're here, the equilibrium would say, I want this all to be reactants. I don't want the NO, but at low temperature, nothing happens, okay? So if you exhaust this in the air, it's not an equilibrium, but if it was, by the way, if at room temperature, the equilibrium would be a lot of NO, we would have a lot of NO here. Okay, it's very simple because, NO, N2O2 here have been around for some time here in the atmosphere, okay? So it wants to go down, but it can't, and that's why in the catalytic converter, you just make the activation energy of this very low, and so you make the reaction fast, so it tries to go to equilibrium, okay? Maybe also in this catalytic converter, you don't get all the way, but maybe, if you get to something close to here, 10 to the minus 2 ppm, 10 to the minus 8. You know, that's very small already. Okay? There's another example here for a hydrogen system. Hydrogen system, so this other reaction we had, H2 plus O2 goes to H2O. Now it gets a little more complicated because you need to invoke the coupling functions again. This actually, you know, computing this thing here is very easy again, but to relate H2, O2, and H2O, you need to use coupling functions. Again, this is not PO, this is P naught, this is the P0. Okay, so here we just use the element mass fractions again to relate the different mass fractions to each other. We don't want to go through this, but at the end of the day, this is the equilibrium temperature. And one thing is interesting is mentioned here. Earlier, first lecture, we talked about complete conversion to products. Complete conversion to products is nothing else than equilibrium constant goes to infinity. Okay? Equilibrium constant goes to infinity means this ratio here is infinity, which means XA and XB are 0, you know, and this here is large. So it's complete conversion. Okay? So this here shows for hydrogen the difference between equilibrium and complete conversion. And you see, this is not very much. That's what I said earlier. It actually, complete conversion is not a bad assumption. Temperature is a little higher here, as you see, than in chemical equilibrium. But it's only around stoichiometric where it's not good. Again, for hydrocarbon flames, it's very different. For hydrocarbon flames, it's quite good here in the lean, but it's very bad in the rich. It's really bad in the rich. Because equilibrium would tell, if you have a hydrocarbon, methane, equilibrium would tell you methane, at very rich conditions, it doesn't go to CO and then to CO2, but it forms ethane and higher hydrocarbons. So you will form a lot of higher hydrocarbons. So this is all an endothermic process. You will take out energy here, and the equilibrium looks like this. You have a big dip here of energy and a very low temperature because of that in equilibrium, which is not the same as what you have in reality, because you never have the time here at rich conditions in a flame to go to equilibrium. Okay? Good. So here, for this hydrogen system, I just want to look at the result, the final result. Again, so this is shown here. Now, this NO reaction, N2 plus O2 goes to 2NO. This has the same number of moles in the reactants and the products, so it's not pressure dependent. If you have something like this, goes to C plus D plus E, okay, then you see there's a PE here and there's a P naught here. So there's a P naught that's left over, and it's pressure dependent. The result is pressure dependent. So for the H2 system here, that's what we have. It's pressure dependent because the reaction is H2 plus 2H2 plus O2 goes to 2H2O. So there's one more H here. So it's the opposite of what I showed here in the example. But you see here at constant pressure, higher temperature will give you less product. Okay? A higher pressure will, so here's 2000 Kelvin from 1 to 10 bar. Higher pressure will give you more product. Okay? Why is this? This just shows another result here for other species. I'll skip this, but you can kind of see it from this, at least the temperature effect. So Kp is here a function of exponential minus 1 over RT, and depends here on this delta Hm. Delta Hm tells you in what direction the reaction is heat releasing. So for this reaction, H2 or 2H2 plus O2 goes to products, a reaction that has heat release, delta H is negative, okay? And now if you could take the derivative of this, dk dt, to see how k changes if I change t. And for negative delta H, this will be negative also, okay? Because you have, you have basically, forget about this first term here, forget about this. Let's say there was no, n was 0, let's say. Then the derivative of this is minus 1 over RT squared. And so it's plus 1 over RT squared, and then if this is negative, then this whole thing is negative also. So this means that if I have a reaction that's heat releasing, then a higher temperature will give me a lower equilibrium value. Lower equilibrium value means you get more reactants, less products, okay? And for the pressure, it's similar, or both of these are Le Chatelier's principle. It basically means you have a reaction that has an effect, and the equilibrium always tries to compensate for this effect. So if a reaction makes the temperature higher, then at higher temperature, the equilibrium tries to do the opposite. At higher temperature, it goes more towards the reactants to make the effect milder. Okay, and the same is true here for this for the pressure effect. You see, I have 3 moles, which create 2 moles. Okay, so the pressure over this reaction, you have less moles, so the pressure would go down, and so the reaction tries to compensate for this. Okay, so this is why. You get more product then as a result of this for higher pressure. Okay, so the equilibrium, so both the pressure effect and the temperature effect, they're relatively easy to understand. The temperature effect depends on the heat release. The pressure effect depends on the number of moles. If you have more moles or less moles in the products and in the reactants. The equilibrium always tries to counteract the imposed changes that you get from the reaction in temperature and pressure. Okay, that's what it does. So, okay. Any questions about this? Okay, then. We move on to maybe we can start, we have 10 minutes. We could start to, so the next lecture in your handout, I think, is governing equations. But we'll skip that. So if you feel the need tonight, spend some quality time with the governing equations. But we will skip this here and move to the next lecture. Which is on premixed flames, and here we want to start talking about just the basic kinematics of premixed flames. Okay, I mentioned earlier we distinguish diffusion flames and premixed flames. We start here with premixed flames. In general, premixed flames are more complicated than non-premixed flames. Although, it might seem differently in the beginning. But so we'll talk a little bit about some general things. We talk about the kinematics for steady oblique flames. Then we introduce the concept of a burning velocity. Once we know the burning velocity is basically the speed at which a flame propagates, normal to itself. Once we know what the burning velocity is of that front, then we can also derive an equation for the dynamics of such a front. And so we'll do this just briefly. Will become important later on when we talk about turbulent combustion. And then we talk about a few special effects here at the end. Of this, special effects means the burning velocity is influenced by the curvature of the front itself. It's influenced by stretch effects, by the flow field, and there are certain instabilities here, mainly the thermodiffusive instability and the so-called hydrodynamic instability. And we'll talk about these only very briefly. I just want to introduce the concepts to you so that you know, when you hear the terms, that you kind of know what it is, okay? And what it does. Okay, premix combustion is used in combustion devices where high heat release rates are desired. I mentioned earlier, internal combustion engine for a Otto cycle, you assume the heat release is all at constant volume, okay? And that gives you the highest efficiency. As long as the heat release is not at constant volume, the heat release, the thermal efficiency is a little lower, okay? So the faster the combustion process in a gasoline engine or spark ignition engine, the better. And so premix combustion, that's the right thing here. It makes combustion devices small, it creates low residence times and so on. Small combustion devices is good. For example, an aircraft engine, you want to have a small device, but in an aircraft engine, if you use, you don't use non-premix combustion because premix combustion is not as stable. So here, example is SI engine, stationary gas turbines. Why stationary gas turbines? Because if you have premix combustion, let's say it's fully premixed, and you run it lean, then lean, you get no smoke emissions. Smoke comes from rich combustion. Lean also means, as we saw earlier, think of the mixture fraction plot, temperature as function of mixture fraction. You go to very lean, small mixture fraction, you get very low temperatures, okay? Low temperatures, think of what we just said, gives you low NOx, okay? So lean premixed gives you low NOx, low, no smoke, very good. Only problem is that you might get combustion instabilities. There's also a lecture this week on combustion dynamics by Professor Leuven from Georgia Tech. He'll talk about some of these things. So, so smoke-free, low NOx, very good. But, of course, as soon as something is pre-mixed, it's dangerous. There's a chance you get an explosion. For some reason, you might get a spark, you get an explosion. The other thing is, just think about it. Let's say I have a tube, okay? And I want to burn in the tube. And I mix fuel and air in the beginning of the tube. And now fuel and air, they flow through the tube, and I light this off, and now you get a flame that propagates into this tube. Now what I want to do, I want to make the velocity just large enough that if the velocity is too slow, then the flame will burn all the way into the premixer. Maybe premixer is a big volume, we call this flashback, you get an explosion, okay? But on the other hand, I need to make the velocity fast enough that I don't get flashback. But if the velocity is too fast, faster than the speed of burning, then you will blow the flame out and blows off. Extinction, if you do that in an aircraft engine, I always use this example. I like this example. No good. Everyone, you can feel it in your heart that you want the engine to burn. If you're in an aircraft, you want the engine to burn. You care about emissions. You are good people. You think, I want low NOx emissions from this engine. But really, I want it to burn, okay? Okay, so that's why in an aircraft engine, you just don't do this. You don't pre-mix fuel and air because it's just more stable. It's very hard to blow out a world-stabilized non-premixed flame. You can blow out. Then also, when you go very lean, you get these instabilities, and they can be very violent because these instabilities also, they're self-accelerating and so on. This nice picture here is from my colleague Godfrey Mangel. This is actually PIV here having particles in the flame. So you see the streamlines. And at the same time, here is a PLIF, laser-induced fluorescence signal, I think, of OH or something, or CH, that just shows you the reaction zone. So again, you see, so it's just a cut through the flame. You see how the flame is really, really thin, in premixed systems. Okay, so premixed flames are typically blue because there's no smoke. The orange color that you see in a cigarette lighter comes from soot. Soot particles, basically, it's basically carbon particles that are glowing, and that's why they look orange. And here, you know, in premixed combustion, you don't have soot except you go very rich. Then you get soot also, but no reason usually to go very rich. So typically they're blue. The blue color here comes from so-called chemiluminescence of C2 radicals and CH radicals, where C2 radical is in combustion is not so important. Very small concentrations in most chemical mechanisms. You wouldn't even find these, but that's what you see with your eye. One here is a little lighter, one is a little darker, but you typically get this blue color. So this here is a so-called Bunsen flame, where you have a fuel air mixture here from the bottom, and you see it cause a flame like this. Now what you know, I mean just from experience, if I increase the flow rate, what happens with the flame?
It elongates.
Yeah, it gets longer, and if you decrease flow rate, it comes back down, the angle gets more shallow, and ultimately, you know, it will move up into the burner maybe. And yeah, this is a turbulent premixed flame here. Using a flame holder, the jet flame here is very easy to extinguish again, to blow it off, and this is why this uses a pilot burner here in the bottom. Okay, so let's see. Yeah, maybe we have 2 more minutes. Just how does a premixed flame look like? What's the structure of a premixed flame? You have fuel and air. They come here from the left, and they are mixed. And then you have the flame somehow converts these two products. The way this works is that fuel and air, they diffuse here into the reaction zone, and the temperature here behind the flame is high. Okay. Now you have behind the flame you have high temperature, and you have products and ahead of the flame. So I'm the flame now. Over there is all burned, and here's all unburned. How does the flame move into the unburned? The temperature here behind me is very high, there it's low. I have fuel and air over here, but they can't burn because they're cold, okay? Cold doesn't burn. So what happens is I have transport now, just heat conduction of the hot products into the cold reactants, okay? So I heat in the preheat zone, so-called preheat zone, I heat up the temperature, I heat up the fuel and air, up to an ignition temperature. It's called an ignition temperature here. Some temperature, and we'll see later on exactly what that is, up to a certain temperature where chemistry now takes place, and now it will start reacting, and it will just convert everything to products and increase the temperature again, okay? So now I'm here as a flame. Now I heat this stuff up again, okay? Then it starts burning, and I'm here. So that's it's kind of the interaction of this heat transfer process and the chemistry at the second, the subsequent chemistry. So the fuel then, the radicals involved in all of this. We'll see later on how this works. And so typically in a flame you consume all the fuel. Doesn't matter if it's lean or rich, you always consume all the fuel. Oxygen, in lean flame, oxygen is left over. In a rich flame, what's left over? CO. Typically you convert everything to CO, and then the CO in the rich flame is left over. Okay, so that's how a flame works. So maybe, see I have some arrows here that show all this. So maybe we'll stop here, and then next time we talk about, tomorrow, we'll start talking about these kinematic balances, and then we move on to flame structure and talk also about diffusion flame. All right, thanks, and I'll see you tomorrow.